ちょっとやめにします。二度テストとか自分でやることでしょ。はい。はい。OK です。Thank you.
So, good afternoon, and thank you for waiting. So, it's a great pleasure to have Professor Seiji Sugita from the University of Tokyo. So, Professor Sugita has received his master's degree in 2092 from University of Tokyo, and he moved to the United States to his PhD degree, and he got PhD in Brown University in 1999. And then after spending a few years, he moved back to Japan as a faculty, and he became associate professor in University of Tokyo in 2004. And then he became full professor.
Don't worry about the details. Okay. Yeah, thank you though. Yeah, please. Yeah.
So, as you know, the Hayabusa2 is a very famous spacecraft from Japan, and Sugita-san is a PI of the camera part, which is the most important part of this project. So today he'll tell us about the detail of the evolution of asteroid Ryugu and its parent body constrained by Hayabusa2 observation. So please welcome him first.
Thank you. Thank you, Okurama-san. Thank you for inviting me for this wonderful university. This is my first time to come to Taiwan, National Taiwan University. I've been only to a Taiwan Central University for planetary applications, but this time it's a very great pleasure to have a chance to introduce my research and our mission work. Okay, and then let's see, guy showed me how to press this thing. You know, I'm a PI, but oh yeah, good. Instrument, I'm not really good at instrument. This is as you can see, it's a lot of authors. It's a large project, international project, and this is a highlight of our Hayabusa2 mission results. And then I'd like to talk about three different things. First one is a mission history. This actually dates back from the previous Hayabusa. A second thing is the Hayabusa2, what we did, how we are doing. And the last thing, which is the most important thing, is a scientific result we think we learned from the Hayabusa2 mission. And then hopefully this leads us to understand the solar system evolution, possibly the more larger planetary formation processes in general. Okay. Before we talk about the Hayabusa2, I'd like to mention a little bit about the background of the Hayabusa series. I don't know how many of you know there's a predecessor called the Hayabusa mission that was launched in 2003. So it's like 16 years ago, and that we used a small rocket with an ISAS, and then 2 years later, the spacecraft Hayabusa arrived at this little elongated small asteroid. The diameter here is about 500 meters, half of a kilometer. It's quite small. And then they made a touchdown here, and then we came back to the Earth. But there was a lot of technical difficulties of this mission. The reaction wheel had a malfunction, and then the thruster had some problem. But somehow the engineers could really bring back the spacecraft back to the Earth. And then here's the actual capsule. From the capsule, we had a very small but many pieces of this asteroid. That was the first sample return for the human being from a asteroid, the small body of the solar system. And then that was received really well by the public, and that really led the funding of Hayabusa2. The talking about money is not something very important for science, but in real life, getting a large mission has to really come up with some kind of money. And then this is one example how major decision can be made. This is the main spacecraft going through the atmosphere. And this is a capsule that was released from the Hayabusa. This was made so that it withstand a lot of heat during the re-entry. of the into the atmosphere, and that has a small amount of a sample of asteroid inside. But the very large flash of light came from the main spacecraft because the main spacecraft was not designed to withstand the heat. If the spacecraft is in a really good situation, it was gonna leave the there's somehow NASA logo. It's a JAXA mission, but I always make a joke out of it because NASA took the image of the JAXA capsule coming in and then claims an NASA thing, but this is really a JAXA project. But I always leave it here because it's kind of funny. Okay, but those guys who took the pictures of the NASA AIMS was a really good fan of Hayabusa2. Anyway, then we gathered the sample. Well, I wasn't really part of the mission, but I can say we. Very small amount size of a grain was found. This is about less than 1 millimeter of a diameter. Very teeny, very small fragments. And the scientists really learned a lot of new things about the surface processes of a S-type asteroid. S-type asteroid is a stony asteroid. The material is very made of a silicates. Not much water or organic, stony, and so anhydrous silicate petrologies and then condensation process is something we can learn. But the most interesting thing or important thing for this type of mission was the difference between the interior of those grains and the surface of those grains. What we see from ground-based or even spaceborne telescopes to look at the asteroid spectra is looking at the surface. But what we are interested in is the interior bulk chemistry, bulk isotope, mostly chemistry. Chemistry translate into the spectra. And then the spectra is something we can observe with a ground-based telescope. If you can use a ground-based telescope, we can observe a lot of different asteroids within the solar system. And then, or the main belt, a near-Earth asteroid, or other small bodies. If you can connect the bulk composition with the spectra, with the ground truth, we can study a census or population study, what kind of material is distributed where in the solar system. That really allows us to understand the formation process of a solar system. But because there's a solar wind and then a cosmic ray bombardment, micrometeorite impact, and those alter surface of those grains, and then the apparent spectra of those material look quite different from the fresh surface of a meteoritic material. We kind of know, even before the Hayabusa arrival to the asteroid, through the comparison between meteoritic material in the hand and then telescopic spectral observation. Those are quite different. But we didn't know what kind of difference is there. We know it's different, but how different are these? What's really causing a difference? So that really stops us making a further inference of a compositional distribution within the main belt and other parts of a solar system. And then Hayabusa, the original, I think resolved this question. This is really so-called space weathering, and then we now know what kind of spectral change we have from the space weathering on very, very top surface. The length here is about 20 nanometers. This is a 1/50th of a 1 micron. 1 micron, as you know, is a 1,000th of a millimeter. It's very small, but it makes a huge difference in the spectrum. Okay, so that was the number one. So another point I want to make here is that even with a very small amount of sample we returned with the Hayabusa, we could learn a very new thing about the asteroid material. Then the next challenge was to go to the so-called C-type asteroid. C stands for carbon or carbonaceous. That has a water and then organics. those materials are much more sensitive to a temperature difference or compositional differences. If we can bring a sample with a carbonaceous material from asteroid belt or near Earth asteroid to the Earth and analyze the thermal history or possibly pressure history, we can learn about what was happening in an early stage of a solar system evolution. And this is one of the recent paper by the Mayo and Carey published in Nature 5 years ago. But the recent popular theory of a solar system evolution stipulates that large planetary bodies like Jupiter and Saturn may have moved from an original position toward the sun all the way up to Mars orbit, and then pushed all the planetesimals going away to the either internal area, inner area of a solar system, or ejected away from a solar system, and then make the terrestrial planet formation region much narrower than without such a excursion. Then eventually it goes back to its final position, which is much further away to the sun. This explains a couple of different things. One is the confinement of a large planetary body formation, and explain why Mars is small. But the second thing is that those larger bodies could be formed much closer to the sun than the current position. As you know, the Kepler's law stipulates that Keplerian orbital motion takes longer as you go further away from a central star. So formation, and then the formation process of planetary formation is proportional to pretty much the Keplerian motion. So when the planetary bodies are formed much further away, where the Keplerian period is longer, the formation time for planetary bodies are much longer. This is one of the problems of a planetary formation theory, not for these terrestrial planets, but those icy giants. Those are estimated to be formed more than 1 billion years, sometimes 10 billion years. It's impossible to explain why it has a gas envelope that was made when the solar system, solar nebula was still left in a outer part of a solar system. And then possible excursion of those giant bodies may be a solution. But this is a little far-fetched story to me, because there's no strong evidence to support that those bodies have been really changed. I mean, I can understand that if this assumption is correct, such explanation could be true. But where is the evidence? And then one of the possible evidence is here in the asteroid belt. It's very difficult to find where those individual large planetary bodies was formed early on, but because those are just single bodies. But asteroid belt has millions of bodies. It has a gradient of a spectral composition. If you really, it's very difficult to make the certain type of a gradient of a distribution unless your model is really correct. The degree of freedom of those asteroid belt or Kuiper belt that has a lot of members is more difficult to explain unless the model is correct. If you have only 1 or 2 bodies in there, if you place on one important bold assumption, you could come up with some model that can explain the observation, because the number of observational factors is very small. So asteroid belt, understanding asteroid belt is really considered a very important piece of information that tells us about the formation process or the original initial condition of a solar system. That's why the small body mission is very important. That's my understanding, and then my colleagues also agree with this. And then how do we really get the answer? That's a real question. And we hope to come up with some answer by the end of this mission, and then I try to offer you my version of the answer by the end of this talk. Okay, and I think I talked a little bit too much, so skip a little bit. But this is well, maybe I have to still talk about. This is one diagram published a long time ago, 1993. This is heliocentric distance, the distance from the sun to the outside of the solar system. This is the diameter of an asteroid. This is one example, but the contour shows the temperature, peak temperature of an asteroid. As you can see, as you move away from the sun, the formation time gets later and later. And then we'll have to introduce a new concept. Aluminum-26, it's a short-lived isotope that breaks down, decays by making a gamma ray, generate a gamma ray, and then decays into different element. But in the process of it, it generates some energy. And then the heat or energy heats up those asteroids. And aluminum-26 has a very short lifetime, 0.72 million years. The lifetime of a solar system, as many of you probably know, 4.5 or 4.6 billion years, much longer than the lifetime of aluminum-26. This is comparable to the formation timescale of those bodies. So depending on where the formation was, the initial amount of aluminum-26 that was captured at the time of formation of asteroid varies a lot. And then if that was formed early on, closer to the sun, aluminum-26 has not been decayed. So lots of energy is formed, generated after the formation of large body. The lots of energy will be kept inside the body, therefore erase the temperature. And you can expect that silicate gets melted, the iron meteorite and other bodies can be formed. But when you see things beyond this certain temperatures, no melting of silicate, only ice could be melted, and then clay minerals and other things are formed. But those are similar to what we expect from a carbonaceous chondrite. Those are very similar to a C-type asteroid. And beyond that, there's no melting whatsoever because the asteroid is formed much later on when the aluminum-26 is all decayed and no heat is left. And then this is close to a comet. So this is one way of explaining where the comet is formed, where the C-type asteroid is formed, where the S-type asteroid, where the metallic asteroid is formed. But as you can see, there's a vertical contour because aluminum-26 decays so fast that if the size of an asteroid is larger than maybe 50 kilometers, all the heat is contained. So size doesn't matter. All the heat is generated. So the composition of variation should be a very strict function of a heliocentric distance here. But what we see here is that there's a major distribution or gradient of those spectra. So this vertical structure is not seen. So that's why a lot of scientists think that this gradient is a remnant of a dynamic stir-up or a disturbance by the large bodies like Jupiter and Saturn and so forth. So this is one key element of solar system formation. But one major question is this a CH, a C, whatever spectral type really represent what we have here in this theoretical prediction? Is this the evidence for the melted ice, or is this a melted ice signature? We don't know. What we see is a spectra. We don't know the difference between the actual composition and the spectra. But if we get the actual sample from those asteroids, we can make a good comparison, direct comparison. Then we can make an inference or the comparison between the theoretical calculation and this kind of observation. So this is what we are trying to achieve. And making I think I'm gonna skip this part, but after establishing that kind of a spectral and compositional relationship, understanding the origin of water to the Earth, or material circulation within the solar nebula, or parent body alteration processes, those are much more straightforward than without such understanding. So this is the ultimate questions like the answer. Okay, and the next thing we should think about is the subsequent processes that change the spectra of asteroid. It's a little bit more details, but the what I just showed you is this stage. Primitive body was formed, and aluminum-26 makes heat. Heat induces aqueous alteration. The chemical reaction happens, but after that, impact happens and it disrupts the body into small fragments. It makes a so-called rubble pile. It's a bunch of debris come together, makes a new smaller object. Then it may come closer to the sun, and sun heats up the surface of asteroid, space weathering. Lots of processes happen. So what we see here is these guys. But what we like to know is this process. This process holds the interesting earliest history of a solar system that really sets up the initial condition of a solar system. Okay, so it's a long, convoluted story, but that's why we have to go to the asteroid and then analyze the details of manifestation, surface manifestations of these convoluted processes. Okay, all right. I think I'm gonna skip this, and then so then finally I'll just show you the computer graphics animation of what we're gonna do with the Hayabusa2 to try to answer that complicated questions. This is the target marker that has a reflector on it, and then it was shining, but that's because, you know, I think I have to stop here. The flashlight was shining from the spacecraft. That's why it was shining. And then by looking at this self-reflector, the spacecraft can capture the surface of asteroid. Surface of asteroids is moving because of its own spin, but when the ball is landing on the surface, it moves with the asteroid surface. So it can capture its own velocity, then modulate itself, and then makes a landing. And then now it's landed. Lots of things happen. That's why I stopped that. There's a bullet stored in this capsule system, and then at the time of touchdown, it shoots the bullet. It's about 1 centimeter in diameter. It's made of a very heavy metal that's not really common in planetary bodies. So its contamination, possible contamination, is not going to induce a problem with the geochemical analysis when we get the sample back. Then when the impact happens, there's a crater formed, and then ejecta, so-called material ejected from the surface, will come back to this horn, then gets into a little small orifice leading to the small capsule in this system. Then the material gets trapped in the capsule, and then we shield the capsule and then bring it back to the Earth. And only this section is a capsule that gets dropped, and then, as I showed you in a motion picture with the NASA logo, this portion gets into the Earth. and this is how the system goes. Okay, then the thruster goes, and then the spacecraft goes back. The duration of the touchdown was only 1 second, so everything happens in a very short period of time. And then now it's a crazy thing. It's a detonator. There's a little explosive inside of this little capsule. It's about 30 centimeters across. I was dropped from the main body of a spacecraft, and then spacecraft leaves the dangerous zone and then goes to behind the asteroid, so that this one, when it explodes, lots of debris is formed, and then the spacecraft is hidden in a safe area of asteroid. Then after everything happens, we go back to the above the impact site to make a measurement, and then drop some ball, and then try to capture some sample, not inside this crater because this is way too dangerous to do, but some material excavated from the impact. And then right now we have done the first touchdown, and then we also finished the impact experiment. Well, I just had this one, yeah. So this is that was a computer graphics, but this one is a actual movie. Oh, no, you are seeing only this one. How can I get this thing? Oh, okay. Hold on. I'm just looking at my. All right. So this is what I wanted to show you. So this is sample horn. It touches the surface of an asteroid, and then some debris comes, and then it was a very tiny moment. Lots of debris came, and then lots of fragments came into this horn. We don't know, but judging from this movie, it's really obvious that a lot of things came in, and then I think they shield the first capsule, and then I'm pretty sure that there's a lot of fragment inside, and I didn't think we were gonna see that many small fragments. I was really, well, if a smart person would really guess, but that was much more than at least my expectation. But oh, that's another thing still going. All right, this is kind of slow, but yeah, let's see. Yeah, a lot of things happened. So that one was successfully done. And then I don't have the picture of SCI impact image in my slides, but yeah, I don't need. Oh, I thought there was another motion picture. Oh, that's different. Yeah. All right. So I'm gonna skip this. Okay, so I'm not gonna do this thing again, but just wanted to tell you that we finished the impact, and we finished the first touchdown, and then now we are in the process of selecting where we're gonna go for the second touchdown. In this computer graphics, we were going to go to this inside a crater, but it has some risk. We have a material inside of the capsule. It's very important to bring back sample without really losing the spacecraft. But it's also important to have a challenge to get the sample excavated from the newly formed crater that doesn't have the space weathering. the depth of excavation is quite large. We don't know the official number, but my guess is it's probably 1 meter or even larger, depending on where we go. This is not going to happen again. Right now we are trying to decide if you're gonna cancel this second touchdown or we're gonna go to near the crater. It's not really ruled out that going to the inside of the crater is also another option. And then we will have to make a decision soon. Otherwise, the timing will be lost. So this is where we are, right? Okay, so this is the basic outline on where we are in terms of asteroid, not asteroid, but the mission of Hayabusa2. Okay, I think I'm gonna skip some of the asteroid family thing, and then I will show you. Well, let's see. All right, but I think I have to, stay on this track. Okay, I'll finish at 15 minutes and have maybe 5-10 minutes of question time. All right, and then now I'll switch gear toward the more real science result. We wanted to answer many different questions, starting with the origin of water and so forth. But the first thing comes first. We cannot answer those fundamental questions without really answering more superficial questions, more elementary questions. One of the elementary questions is, where is the Ryugu's parent body? Ryugu is the asteroid we visited with the Hayabusa2 spacecraft. The spacecraft, or the Ryugu, has an orbit from 0.95 AU to 1.4 AU. That's about somewhere between the Earth and Mars. Many near-Earth asteroids has a similar orbit, but lifetime of those near-Earth asteroids is very short, like 10 million years. Before that, most of them, well, pretty much 100% of them, well, not 100%, but most of them comes from an asteroid belt. And then many of them come from this inner belt. And then that's probably where the Ryugu's parent body is located. And then there are many so-called families in inner belt. Many of them are S-type asteroid, all stones. I mean, anhydrous silicates. But some of them are exhibiting C-type spectra, but not that many of them are C-type spectra. Only 5 of them exhibit the C-type asteroid. And then some of them are too small, too confined, actually too young. The age of a formation of asteroid family is too recent that their fragments did not reach those resonance zone. Unless you reach the resonance zone, the fragment doesn't come to the nearest orbit. But those large dispersion families, one is Polana, another one's Eularia, third one is Ergani. Ergani is still smaller, but large enough to be a candidate of those family members, source families of Ryugu. Those are large, strong candidates of Ryugu, and also Bennu for the NASA's OSIRIS-REx mission target asteroid. So we're trying to tie our Ryugu's asteroid to those family members. And the first result we obtained as soon as we arrived at the Ryugu, the spectra, this is really heavily stretched, but they turns out to be very flat. And the major difference between Polana, Eularia versus Ergani is the absorption over here. Well, can you see there's a little absorption compared to this continuum? It's still like a little wiggle, but there's some depression over here. this is a typical spectra of some type of a hydrated mineral. It's called serpentine. You don't need to know the proper noun, but it's a combination of a rock and water. It's very typical on many planetary bodies. But it's a little bit depressed here, but this is definitely within the error bar. And we decided that this is so much closer to Eulalia or Polana than this. The spectral slope is not close between Ryugu and Polana, but the fact that there is no strong absorption at the points of micrometer has many things in common between Ryugu and those two bodies, not over here. And then this origami would have counterpart meteorites on the Earth. It has been well characterized. We know what kind of composition they have, but we don't actually know what these planar and the Eulalia has in terms of its composition, the chemistry, all that things. So it was in a way disappointing because we didn't know which asteroid meteoritic counterpart we are analyzing, but it's very exciting in the sense that we arrived at asteroid that we don't know much about. As a matter of fact, this asteroid has really large members. The CB type, B type that we arrived is a majority member of a inner asteroid belt, and then we don't have a very good counterpart in the meteorite collection on Earth. So we may be able to bring back some sample that we don't know much about, but still this is a very major member of a solar system. So this is one big finding we had. And then one candidate for hypothesis or scenario for this Polana, Eulalia, Ryugu type spectra is a so-called thermally metamorphosed meteorite. Those are not really common meteorites. It's found not only, but mostly in Antarctica, not somehow found in Saharas and other area on the surface of Earth. We don't know exactly why. Well, there's some hypothesis, but those are very similar to what we see in Ryugu compared to other so-called more typical carbonaceous chondrite. So it may be opening the new door for the solar system material science. My interpretation is that those are more original carbonaceous material, and then the evolution stopped right there. But after having an additional thermal metamorphism on those asteroids, those material gets darker, and then the spectrum gets really flat. Then that becomes Polana and Eulalia type spectra, and then sits in an internal edge of a solar system. And then that's what we really actually see in surface of Ryugu. But I'll get back to it later. All right. Next finding we had was many impact craters, just a hole. I don't know if many of you are interested in the holes in the surface, but meteorite hits on the surface of asteroid. This is very important to us because we know how impact happens. The probability of a hitting rate, we know. Well, not like very precise fashion, but the order of magnitude estimate is really established. And there's no that many impact craters. That means that the exposure of a Ryugu surface is not very long. That means that the surface of an asteroid is heavily altered or disturbed, or like a resurfaced, it's called. There's a lot of circulation of material. Lots of mass motion is going on. So that means that the surface of Ryugu is relatively fresh. I'm not going to go into the detail, but based on the impact rate on the number of craters we find on the surface of Ryugu. Actually, the smaller craters, this is in a kilometer, so this is 100 meters, 10 meters, and several meters of small craters, very small in population. So resurfacing rate of those shallow depth that would erase the small craters is very active. On the order of, this is 1 million years overturn. From here to here is a factor of 10. Another factor of 10 makes it here. So this is 100,000 years, even less. So this is actually an upper limit. The lower limit is over here, 1 million years over here. Factor of 10 is over here, another factor of 10,000. So this could be as young as several tens of thousands of years. Very, very young, particularly compared to the other planetary bodies, Mars, Moon. So the surface of those asteroids is surprisingly young. This is one new finding. Another thing is spectroscopic properties. There's not much spectral difference. This is a distribution of a reflectance factor. It's almost like the darkness, okay, or brightness. The ratio of reflected light is only 0.01 something. It's like 2% of a reflectance. So it's as dark as any dark material. I don't think this is like a 2%. This is probably like a 10% or a 5% of reflectance. Surface of Ryugu is darker than blackboard, very dark. And then also the distribution is very narrow. Everything similar to each other. Only one exception we thought we found is a continuum slope map. It's like a blue versus red, very general difference. That itself is also very gentle. There are some troughs, equatorial ridge, and the polar region that's a little bit bluer than the rest. But that's pretty much it. And then the surface is very uniform, probably because the surface is gardening very actively. And then it's really well mixed. But those areas correspond to topographic high. Those material in the ridge tend to fall to a topographic low. And actually, the pole is also topographic high. It's relatively round object, but it's a little bit elongated on the polar region and then also equatorial region. When you look the Ryugu from the side, it looks like a kind of square, what do you call it? It's okay. Yeah, like some two diamonds shape. The polar and the ridge are a little sticking out. Those areas turns out to be a little bit bluer than the rest. So bluer material is probably a little bit fresher. And then I'm gonna skip a little bit, but possibly this is due to the effect of a solar heating. The material that is accepting received a lot of solar heating may have become redder, and then fresher material may be bluer. This is still a work in progress, but that kind of change is seen, but the difference is very minor, as you can see here. So wherever we gather the sample, we will get a solar heated material, solar unheated material. So this is what we think we will get. Moving on to another thing, getting further into detail. I don't know if you can really see here. I don't think I showed you the entire picture of a Ryugu, but the bunch of large boulders. Those objects are boulders, big rock. Most of them have this kind of a morphology. I think there's not many geologists here. It's a physicist mostly. So maybe you're not really interested in the shapes of rocks, but we can learn something about the history by the shapes. One example is here. These guys are blacker than these, and then to me, there's an irregular layered structure than this one. This has a little bit smoother, brighter surface, and this is much smaller. These guys don't have a similar layered structure. And this one is the largest boulder. It doesn't have a splotchy structure or texture or those kind of layers, but it doesn't appear to have evaporators. And all of them have a distinctively different spectra. Those are really spotty. Everything else is a regolith. Regolith is called a surface sands and pebbles, very small, fine grains. Those have the spectra very close to the average of Ryugu, but those boulders have a quite different spectra. And those probably have gone through little different thermal history or some kind of history other than the regolith. And then this regolith spectra is close to this type 1 boulder, which is the this one. This comprises of 90 or 95% of the entire boulders population of Ryugu. So bulk of Ryugu material is this guy, and the mixture of a minor component of this and this and this. And then that's probably having some kind of a history of Ryugu. And then another interesting finding we found is that when you plot that boulder color data into this reflectance and then the slope, the different boulders actually end up to line up in a single line. I mean, it doesn't mean much, but yeah, this is what we observe. This is very similar to what you probably observe in any kind of observation. Is there any trend? Yes, there is some trend. Type 1 boulders here, type 2 boulders is here, type 3 boulders is here. Morphologies are quite different, but somehow they line up together. And then one large giant boulder called Otohime formed its own trend, different from this major trend. We don't know exactly why. Well, we have a little hypothesis, but the two different trends. This is probably reflecting some kind of a history of Ryugu. And then we moved on to another analysis. It's called a principal component analysis. I don't know if this is something you learn in physics or math, but when you, oh, you're graduate students, right? So some of them you may have learned about principal component analysis. It's just a math. It's not really based on the physical assumption or modeling, but the try to get the not an end member, but the some kind of end member that extract the largest amount of variance of the variation in the sample group. One type of mathematical way to decompose the elements into factors into end members. And then biggest end member is a slope, but the second biggest end member is over here. PC2 is here. It's the 0.7 micrometer absorption. This way has a bigger component here, and then this PC3 principal component 3 has a absorption here in the UV range. This is a specific observation and something you don't have to really be worried about. But what we see on the Ryugu is that this is over here. It's a regolith is a black contour, and those color squares is a boulder distribution. Again, you can see some linear trend here and another trend here. Those are boulder type 1 through 3. Boulder 4 forms its own shape. What does it mean? the rest of a very busy diagram shows the distribution of a main belt asteroid. These are CBC type asteroid that doesn't have a absorption of hydrated minerals. This one is a CH asteroid that exhibit very clear signature of serpentine. That's one kind of a hydrated mineral. And those are very similar to the typical carbonaceous chondrite we have on the surface of Earth. We don't have a counterpart of these guys. And then one possibility is that comes from this trend. When you heat up carbonaceous chondrite in an oven from 0 degrees to 400 degrees, 500 degrees, 600, 700, comes back. It goes along this track. It makes a transition from a CH type asteroid spectra to CB or B type asteroid, goes back and forth. And then Ryugu is located exactly in this thermally metamorphosed domain. This is one school of thoughts, but the Plana Eularia also sits in the same place. That's why some of us think that this entire population, it's about like 50% of asteroid belt is, well, in terms of C-type asteroid, is a thermally metamorphosed asteroid. Well, we don't know yet, but there is a correspondence between, well, agreement in the spectra between Ryugu and those thermal CB type asteroid, and also experimental spectra with overheated chondrites. The agreements of those three really bring us a hope that once we get the sample back from the Ryugu to Earth, we can test this hypothesis. If my inference is correct, the Ryugu may have been a thermally metamorphosed asteroid, and then it may have received a lot of aluminum-26 heating and so forth. And then maybe tells us about the age of a formation of a parent body of Ryugu. Okay, it has to be very early on when the aluminum-26 was still there in the parent body of Ryugu. Okay, the last piece is that after the possible metamorphism, there may have been a lot of impact fragmentation. When we are looking at the very high resolution images, we saw lots of layered structures. It's not really perfectly layered, but it's irregular surface, but you can see lots of layers. And also there are a lot of fragments inside of one boulder. It's not one fragment sitting on the top of another boulder. It's within one large boulder. Large class, angular class are embedded. It's called a breccia. It's typically made by fragmentation and subsequent sedimentation, and then cementation put the fragments together, and then we have a breccia. You see these things on the surface of the moon. It's on the moon. It's an act of the impact, and similar thing may have probably happened on the parent body of Ryugu. I don't think it's possible to have this formation of impact breccia on Ryugu, but probably happened on the parent body of Ryugu. This is what we see. It's not the only one example, similar but little different appearance of impact breccia looking boulders are found on the surface of Ryugu. So it's a quite common process. So putting those stories together, I put this possible evolution model of a Ryugu and its parent body. It's still work in progress. Well, I published a paper, so I have a little commitment. I mean, you can criticize it. I have a little copies of a paper if anybody is interested in taking a look. But compared to the schematic diagram, this is a new schematic diagram. Aqueous filtration probably happened. Then some kind of a heating happened. I believe this is probably aluminum 26. It's not yet proven. Maybe just the impact heating. This is something we have to find out. Then subsequently, major disruption happened, forming asteroid families. One of the family members, well, it's not really fireworks, but yeah, I try to depict the fragments kind of colliding, reaccumulating together to make a so-called rubble pile. And then this may be Ryugu. It could be another. There could be another impact, and then subsequent impact formed a much smaller asteroid. That may be Ryugu, because Ryugu is too small to survive more than several hundred million years. And then Polana and Eulalia is close to 1 billion years. So there's a gap between the possible lifetime and also family formation age. That's why there's maybe intermediate parent body, but that's a little bit detailed. So multiple processes may have happened, but now we can talk about with a proper noun, Eulalia, a planar, a candidate source, and then the age of a disruption is probably less than several hundred million years, and then specific heating mechanism we can talk about. And then there's another different hypothesis that maybe there's no heating whatsoever, but I think it's much less likely. But this is another counter hypothesis that we should really examine when we get the sample. Not gonna really have the time to explain what hypothesis is, but basically this would be very similar to what comet material would be. But if this hypothesis is correct, the constituent material will be very loose, because this hypothesis predicts that there's very little amount of a chemical reaction occurred throughout the entire history. So the cementation between different grains is very loose. But in the process of impact experiments and other interaction between a spacecraft and the surface, appears to me that the mechanical strength of a constituent material is rather high. The material appears to be mechanically strong, and that supports this kind of a scenario that has gone through some kind of a water rock reaction and subsequent metamorphism, and then impact fragmentation, rather than no reaction whatsoever, and then kept everything really cool and then loose. But we cannot really rule out yet, and we will find out when we get the sample. And then, this is a very busy summary. This is the summary of what I just showed you. And then when I end this talk, just to show you how much ordinary non-science Japanese people are really excited about this mission. This is a launch of a H2 rocket. Can you hear the somebody screaming? The guy, it's not me. Somebody who just standing next to me. You're so ecstatic. I was going to record the engine sound, but somehow I ended up recording this guy screaming, you know. But it just shows you that ordinary people, non-science, scientists are really excited about this mission. But then people start clapping. But that was 4 years ago. And then, I think I can stop this. And we are getting some decent science result. I think this is I should show you this picture. This is really good. I should have shown this picture first, but anyway, so this is what's happening, and then this is what I think we learn out of a pipe submission. Next thing is the second touchdown. We may decide not to do it, but we have to make sure, we will make sure that we'll get the sample back. I mean, I don't know if there are some people interested in geochemistry as well as astronomy or physics. Maybe you can have some opportunity to analyze the sample. The sample return will be December of 2020. That's next year, right? Thank you.
Thanks so much. It's a very interesting talk. So we are a little bit running out of time, but it's a very great chance. So maybe we can take a few questions.
So do you have the information of the average density?
That's a good question. I should have mentioned it, but it's a 1.19 grams per cc. It's very light. Yeah, 1.19. Like a 1.2, like a 1, as you know, is water. So it's only 20% heavier than ice or the water, but it's clearly made of rock. It's not really water. So and then the lightest asteroid, the meteorite we have on the Earth is about 2 or 2 point something. So there has to be lots of pore inside, and then that's why it has to be a rubble pile. But if you just put the rubbles together, the pore ratio isn't going to be like 40% or 45%. It has to be extra empty space. And that's probably inside those individual boulders. So those individual boulders has its own pore because it's the impact pressure. So the individual boulders has its own pore inside, and then those porous boulders are put together, become a rubble pile, and that's probably what we see, and then density is very low.
Any other questions? No question for Shiro.
You mentioned about resurfacing
Right.
the object, and it's probably very young. So, what's the energy source of this resurfacing?
That's a good question. Energy source is probably another impact. Seismic shaking. Impact-induced seismic shaking. The trick here, I think, is that those pebbles and boulders are very mobile. It moves a lot. Actually, when we touch them, I don't have the picture of it with me, but just thruster jet, we moved around large boulders. So just a small touch on the surface moves. That's, I think, why the surface of Ryugu is very fresh and actively resurfaced.
Any others? Maybe time's up. So Sugiya-san is staying in Taiwan until tomorrow. So he's leaving tomorrow. So if you have other questions, please talk to him today. So let's have to see him again.
All right, thank you.